All right, let's start. Hello, everybody, again. Thank you for joining me in this fourth and last in a series of live hacking your AWS workloads. My name is Camille. I'm a senior security engineer at Snyk. I currently work at infrastructure as code product. My background is in offensive security, so I have spent some time pen testing and doing security research in a cloud native space. So why are we doing this session? So this session is about common misconfiguration or like initial default settings in AWS EKS services. Misconfigurations are becoming a big problem, mainly because the clouds are being more accessible. There is a way more services we can deploy. And there is multiple ways you can do those. However, they also hide some extreme complexities in these systems, and it's quite easy to make some mistakes. And these reports from this year are some indication of like how organizations are now trying to deal with this problem. So what are we going to cover today? We're going to try to learn how to avoid single point of failures in our configurations. We're gonna see some like sequences of misconfigurations and what are the consequences. We're gonna see how we can detect this misconfiguration early. All of these things are like accompanied with demos, so it's gonna be a little bit of background theory knowledge and a lot of demos. And I hope you're gonna enjoy this. So let's get started. What we are not going to cover, however, today is how we're gonna how Terraform continuous delivery systems work. We have awesome paper written Snyk with engineering better on continuous delivery in infrastructure as code. We also probably seen some demos of how to exploit containerized applications this week. So this demo is not on those specific comments. I'm just going to open my chat window so I can see any questions that pop in. All right, so what is EKS? EKS, Elastic Kubernetes Service, is a managed offering from AWS. AWS will take care of running the control plane of Kubernetes service for you. So as you can see on the screen, there is a lot of complexity in Kubernetes services. On a control plane side, there is the HCT clusters, there is schedulers, there is API service. There is a lot of moving things that AWS will take care of for you. So you don't have to worry about how to make them more reliable. You don't have to worry about how to scale API server. You just need to worry about deploying configuration to your cluster. AWS also will allow you to have managed node groups. So you have two options. You actually have three options. You can either have self-managed workers where you control everything from AMI that goes onto your nodes. You can have managed nodes where AWS kind of pre-packaging all of the AMI configuration, operating system services that run on these nodes, and they will deliver updates to those services for you. And you can also run workloads on Fargate servers, which means each pod, each deployment will run in its own dedicated container. So these are like high overview of EKS. And we say there's a lot of hellos from around the world, so it's good to see people from everywhere. And what is Terraform? Terraform is a tool that allows you to declaratively configure your infrastructure and many other things actually. So Terraform as a core provides a language that allows you to describe the desired state of your infrastructure. In our case, that's going to be Kubernetes services, but you can configure almost anything on AWS with Terraform. Terraform has concept of providers. Those providers are logical implementations of getting your desired declaration to being deployed. And that takes care of making sure that it's that configuration gets deployed correctly and it stays as it is throughout the lifecycle of your services. What we're going to do today a lot is a lot of CLI demos. When you're operating on CLI, you can be safe by using AWS Vault servers to securely store kind of long-term credentials for your AWS APIs. That service will use STS service from AWS to generate temporary tokens that will expire after a certain time. So no credentials will be stored kind of hard-coded on your system. So you're kind of limiting exposure to you. So stay safe and use this service. It's great. So let's get started. What we're going to do first in our first demo, we're simply going to deploy AWS EKS cluster. To showcase this, we have some sample code. So here on GitHub, we have one resource that says AWS EKS cluster. Don't worry about the variables. What we're deploying in the backend is its default configuration. But as you can see, this is quite simple to declare what is very complex Kubernetes cluster with literally 18 lines of code. We're also going to deploy managed node groups. And again, all of these settings are configured to be default. What we're selecting is simply the size of our instances, the type of AMI we want to use. And again, all of it takes around 30 lines of code. So it's quite not a lot for very complex things. So let's see how this looks like in action. Scream in the chat if the videos are not clear, and I will try to make them bigger. But what we have here is we've configured this simple user called James Smith, and we gave James Smith administrative permission to our AWS account. And James Smith will try to deploy Terraform configuration with Terraform plan command. What Terraform plan does, it generates like intended state of basically describe to us what we will be doing. I will share the link to the repo at the end of the session in the chat. So what we can see here is that the plan says that we're going to deploy a cluster. And what we run is a second command called Terraform apply. So with two commands and a little bit of code, we're simply deploying entire Kubernetes service. Now, the reason we pre-recorded this is because deploying infrastructure takes time. So this in general will take around 20-25 minutes. So we kind of skip that bit of it outputting us its progress. And what you can see here in a second, this bit for some reason takes longer, that we have our Kubernetes cluster running. And here we go. So we have 3 nodes running in our cluster, and we're just going to grab some cluster information. Cool. So that's it. We've deployed EKS cluster. This just shows you the power of Terraform, of like how quickly can you deploy very complex thing. So now that we have a cluster, let's jump into our first thing we need to notice. By default, EKS displays, like makes the API service publicly accessible. And this means that anybody on the internet can try to query your service. Now, there is still an RBAC authorization in place, so someone trying to do that will not be able. I think it's being recorded. So someone on the internet will be able to query it, but not access the services. However, considering what's happening right now with log4 shell exploitability, you might understand that it's a good thing to provide some additional boundaries between your kind of backbone services and public interfaces. So it might be a good idea to have these public interfaces disabled. There's consequences to this. You will need to have some sort of internal access to your API, such as VPN. But also there is services on the internet, such as Shodan and Census, that will continuously scan internet endpoints for information about your public endpoints. And for example, our clusters will be accessible. Additional bit to worry about with clusters is what we can do. This is live. So we can grab the public endpoint of our cluster and try to see what information is accessible in literally the self-signed certificate generated by the cluster. So by itself, you might think that it's not a problem that there is a certificate, but if you look in detail of what information is provided, you actually might expose internet IP addresses of your public cloud. So for example, the attacker now will be able to gain knowledge of like what are the private IP ranges of your internal systems. That might be useful in the future attacks. And that information is literally included in subject alternative name of your self-signed certificate. So that's it about the private endpoint. Now, next thing we want to talk about is, as I showed you, we've deployed the cluster with the user called James Smith. We gave James Smith administrative permissions to our AWS cloud. That allowed him to create the cluster. However, the identity used to create a cluster has hard-coded like administrative permission on the cluster that cannot be revoked. That is due to how the AWS IAM integration is configured with Kubernetes EKS service. You can add additional users to be able to access your cluster. However, you can never revoke James Smith permissions. That even includes ability to delete that user. So if I would go ahead and delete the user and recreate it again, James Smith would still have access to our cluster. And to demonstrate this, we have another demo. And what we're gonna do is, just continuing from where we left off last time, what we're gonna do is we're gonna remove all of the AWS permissions from James Smith. But before we do that, we just show you the AWS auth config to prove to you that there is no linked to James Smith identity in there. So what you can see here, that there is a map roles, which basically means we're mapping certain IAM roles to certain permissions in Kubernetes cluster. In this case, we're mapping, by default, Kubernetes needs to map the node instance profile permissions so that nodes can basically behave as Kubernetes nodes. So what we do here, we're just gonna literally disable administrative permissions from JSmith. And we're gonna run another Terraform command to simply remove it. And as you can see here, the Terraform plan says we're gonna destroy these permissions. Before we do that, I'm just gonna demo to you that James Smith still has permissions, and then we do the action of removing them. We have no S3 buckets, so that command was not very representative. But we have policies, so we're gonna list some policies. All right, so we can see that James Smith still has access. And let's go ahead and apply our change. Right, so we have removed all of the permissions from James Smith. So James Smith is still an IAM user. However, that identity doesn't have any permissions. So it takes roughly a couple of seconds for AWS to sync the entire system so that it reflects, but we can just look at the console and refresh it. And as you can see, there is no permission policies attached to this user. And let's just give it like, you see, he's not a member of any group and the identity doesn't have any permissions. And then if we, as you can see now, all the permissions are denied. So that user cannot literally do anything in the account other than kind of validating its own identity. However, as you can see now, we can still access all the resources in the Kubernetes clusters, and that does not go away. Now think about if you're using IAM users in order to do this, and using common names such as James Smith, imagine that user changing a position in your company, or you actually, that person resigns and then new person joins with the same name. If you would recreate that user will have this hidden permission to your clusters. So it is one of those things that you need to be very aware of when you're creating clusters. The solution to this problem at the moment is to try to use either one-time IAM roles that you simply use to create clusters and then delete them, or use dedicated roles, such as roles specifically used to create clusters, and be aware that those have very, like basically administrative permissions on the clusters they've created. Okay, moving on. Let's talk about AWS account multi-tenancy. So in our demo example, and it's a common scenario, we have multiple workloads running together. So what we have in our system, so let's go to EC2 service. We have 3 nodes and we have some internal portal. Internal portal is dedicated service that's not running on EKS cluster, it's owned by somebody else. All of the nodes in EKS clusters are simply EC2 instances. They have the same access to metadata service and any assigned IAM permissions to it like any other instance. And by default, EKS requires those nodes to have certain permissions. Some of those permissions allow it to enumerate information in an account about other instances. Some of them allow it to pull container images from ECR registries, but the dangerous permissions that it allows it to do is to modify network interfaces. And in order to demonstrate the risk of that, in this demo, what we're going to try to do is to use James Smith access to the cluster that he has because of this hidden configuration that allows him to do anything on a cluster to obtain information about the internal portal. So James Smith doesn't have access to internal portal, and it runs in a dedicated security group, as I show you in a second. And that security group can only allow access to itself, which means you need to be part of it. It runs in a private subnet. There is no internet access to this EC2 instance. And what we're going to do now, we're going to use the instance profile permissions that are assigned by default to escalate our privileges. So what we're going to do, we're going to deploy a pod that has AWS CLI installed on it. We're only using the CLI pod to make this demo easier. It can be any pod that has network connectivity, and as long as we can, curl requests to the local API endpoint. So we're going to wait for this to instance this pod to start, and then we're going to exec. So you can basically run interactive commands inside of your pods. And then what we're going to show you is run just normal AWS CLI commands to describe instances, for example. And as you can see now, James Smith, that doesn't have access to anything on AWS, now has ability to enumerate all of the EC2 instances in this account. That's only because that permission is assigned to the instance that the pod is executing on. So our next step in the attack is to obtain information about our target. So we know the target runs with the name internal portal. And we can do this with filters. What we're going to do is enumerate only that instance, and we're going to grab some important information for our attack to succeed. The goal of the attack is to modify our EKS nodes to be member of that security group that grants access to this instance. So that's our goal. That's what we're trying to do here. In order to do that, we need to, first of all, find out what is the security group and what is the address of the target. So we already, as you can see here, grabbing the IP address of the target. And we're grabbing the security group that we want to obtain access to. Now, what we're going to do quickly is just deploy a helper pod that has a lot of networking tooling on it. All we want to do in this simple demo is to demonstrate to you that we can establish network connectivity to this pod, to this target. So we're going to execute this netpod that has ping, netcat, curl, and all of those tools. And we're just going to try to ping our target. And as you can see, because we haven't executed the attack yet, we should not be able to connect to it. And as you can see now, like the traffic is not going through. We're going to have dropped requests. So our kind of security profile is secure, right? So we cannot access internal service at the moment. So let's go to the next stage of the attack. Let's get information about ourselves. So we need to find out which network interface we want to modify. So in order to do that, we're going to enumerate information about our own cluster. And we know our nodes belong to a cluster called deploy demo. And we can, again, use tags in order to enumerate all the nodes. Now, for the attack to work, we don't need to compromise all of the nodes. All we need to do is simply modify network interface of one of the nodes. So we're grabbing the first one in the list. We get our interface ID. And that is actually everything that we need for this attack to work. We're also going to grab availability zone. The only reason we grabbing availability zone is that we're going to force our exploit pod to work on this specific node. And we can use the knowledge of availability zone to target specific node. So we're going to use a command called modify network interface attributes. We're going to give it a network interface ID of our node. And then we're going to say for that network interface, we want that interface to be member of two security groups, the existing one, because we don't want to lose the access to our own cluster, And we're going to populate it with this sensitive security group that is member of the internal portal. And if we run this, as you can see, command succeeds. Like we have now modified the infrastructure, not only enumerated information about it, but actually changed it. And what you see here is that the attack still doesn't work. Now, the reason for that is our pod is running in a wrong node. And we can use the knowledge of Kubernetes configuration to force it to run on a correct pod with the node selector. And we're simply gonna drop in that availability zone. So let's try it again. We need to recreate the pod. So we need to delete it and create it. And then we're just gonna create it again. Exec into it. Okay, we're there. And our ping command should work now. Ta-da. So now we have literally changed the infrastructure of our cluster with default permission that are granted to the nodes in order to gain access to some sensitive resources in our account. So this demonstrates you like why AWS account multi-tenancy, it's so difficult to achieve. There is a lot of inherited permissions everywhere in different services, and EKS and nodes are not the exception to this. So let's say that now we went through this attack and someone has managed to identify there is something going wrong. And if you look at our configuration, and let's see if this is still present or has been overwritten. Right, I don't think so. But having two different security groups on a single node, it looks odd. It might stand out and someone might notice, right? So let's see if we can trace who performed this action with the default configuration of EKS. So the beginning of this demo just goes through examples. So what we're gonna do is we're gonna use a service called CloudTrail. CloudTrail monitors all of the API activity in AWS. By default, it stores the recent history. You need to configure trails if you want to persist this. So I would recommend that configuration. But what you can see here is that modify network interface attribute event was captured by the CloudTrail. You can see that we can see some details about it. So we see what AWS access key was used to perform this action. We can see source IP. We can see details of the activity. So we know what permission was used, like what role was used. From this, we can deduce that it was performed by a node instance. So therefore, the activity must have happened on a node or someone who was able to assume that permission. We can see the date and time of when it happened. And you see the actual details of activity. So we're saying we can see that someone has assigned two security groups to the specific network interface. Now, in our demo, this stands out because there is not much activity. You might not be able to see that clearly on a real-time environment because, for example, this specific action is actually performed by nodes for the right reasons. So nodes need to modify network interfaces in order to provide IP addresses for pods when they join network. For example, this example shows you just normal activity. Everything in here literally looks the same as in our exploit, with the exception of two security groups being added to the interface. So from that on, we might want to move in and see, okay, what happened on our Kubernetes cluster, right? So we want to trace it back. We can go to the cluster and try to look at the events, but events don't have that much information. And this is a demo, so certain things here stand out. However, on a normal cluster, there will be thousands of events that's happening all the time, and you won't be able to spot this simply. What you want to be looking at is the Kubernetes API logs and audit logs. And those are usually sent in AWS to service called CloudWatch logs. However, what you can see here that those logs don't exist. So let's have a look at the Kubernetes cluster configuration. And what you will see that by default, all of those log configurations are disabled. So if you don't think ahead of time, about your need to trace events, you might not be able to retrospectively have those events to look at. Okay. So now that I showed you some of these exploits, what can we do about them? So the first thing we want to be doing is trying to restrict access to this to these policies. And there's multiple ways to do this, and I will show you a couple of those. The one of the ways that won't require you to change your infrastructure is to use network policies that are part of Kubernetes ecosystem. Network policies need to be enforced by a networking engine, and one of those engines that is supported by EKS is Calico. So let's see how network policies can help us prevent this attack from happening. So we have another demo. In here, we're going to show you how quite easy it is to deploy Calico in the first place. So I have a bash script that calls 2 API commands. Now, in your production environment, you will try to manage this properly. You will not be just downloading some manifests from the internet and deploying them. Hopefully, you will have them in a version control system to make sure you can configure it properly. But if you're playing with it, this is how quickly you can deploy Calico. It's just one command and it just works. Now we need to deploy our network policy that will prevent access to the metadata service. Metadata service runs on a link local address, which is this. So what we're saying with this network policy is we want to block all egress traffic. Well, we want to allow all egress traffic with exception of metadata endpoint policy. This allows your services to operate as they would, with exception of accessing metadata service. So we deployed it. Now we're going to execute the same pod and see if we can execute AWS commands. So we're just going to redeploy our pod. And we're going to execute it like we did before. And we're going to try to execute an EC2 described instances command. And because the network policy is enforcing the traffic, this will be routed to a link local address, and the network policy is blocking it. So we just to make sure, we're going to give it a region so it doesn't complain, and you're going to see that it's unsuccessful in trying to reach that. Now, there is a problem with network policies with the fact that it can be easily bypassed by using host networking mode for your pods. So with one change in configuration, you can force your pod to be running on a node network, not within it. And all of those network policies at this point will not be enforced. And it's, as you can see, one line change. We're just going to change host network to true. And I have one question. Yes, AWS CLI is the container that we executing through IT. The dash IT flag, it means interactive. So we basically can, like we have the kind of interacting session with this pod. Now, we've basically made the pod run in a host network. And what you're going to see here is that yet again, we will be able to run the same exploit. We again can access the metadata service. So network policies are great because they don't require us to change the infrastructure, but they are not complete solution, right? So we just shown you how you can easily bypass that as well. So what's the next step? What we want to do is to validate all these requests that are being sent to our API service. Pod security policies used to be the way to kind of enforce what the pods, like what people are allowed to do in the pods, but those are deprecated. So the alternative solution to that is admission controllers, and Gatekeeper is one of those admission controllers that is powered by Open Policy Agent. Gatekeeper allows you to specify rules that say that certain configuration types are either allowed or denied. So in the next demo, we're going to show you how you can use Gatekeeper to prevent pods or deployments or any workloads be deployed with the host network mode. Again, to deploy Gatekeeper is quite a simple command. Again, in a production environment, you would normally use version control system to deploy this so that you can configure it. So we're just gonna install Gatekeeper. And now that we're gonna have Gatekeeper running, the next thing we need to do is define that rule. We need to want to say host networking is not allowed. The language used by Gatekeeper to do that is called Rego. So what we have here is the kind of template structure is used by Gatekeeper to create those rules. In short, we're saying issue a violation, so deny the request if the input object has host network in its spec set to true. So that's quite simple. And if any object that has spec.host network set to true will be denied. So we're going to deploy this. We need to deploy a constraint with it. Constraint will describe what commands apply to this. All right, and then let's see if we can, like, we're gonna delete the pod first, and then we're gonna try to recreate it. Gatekeeper is running on API service, so it's not client controlled. The client cannot decide what they want to do. So Gatekeeper, whenever we send a request to Kubernetes API server, will receive that request first, and then it will decide if that request is allowed to proceed further down the chain in API deployment. And as you saw here, that the request was denied. So the client cannot control it. So it's kind of, it's a good control that cannot be bypassed by anybody other than a person creating rules for Gatekeeper. Now, the limitation of a Gatekeeper is that sometimes you will have pods that will require host networking. Like there might be daemon sets that need to run on a node in order to, for example, to inspect traffic. And you might not necessarily want those to still be able to use those permissions. So the true solution to our problem is that we want to remove that sensitive permission that allows us to modify this network interfaces from every single pod that's running on a node. And the solution to that is to use IAM role for services. What that means is we will remove the CNI policy that allows us to modify permissions, which is required by the AWS CNI plugin that manages the AWS network VPC native networking from, and we will assign that permission specifically to one service that needs it. And we have a demo on how to configure that as well. So in our configuration, what we will do is we will create an instance role for the service. In order to do that, you need OpenID connector to your cluster. Again, it's around 20 lines of code in Terraform. What you then do is you scope that specific role to be only used by a service account that is linked to a specific service. In our case, AWS Node service that is responsible for managing network configuration. That means that any other any other service on a Kubernetes cluster will not be able to assume this permission. And then the second part of it is to remove that policy from the metadata instance profile. We're gonna just simply run Terraform plan now, which will show you that it's gonna say we are deleting this specific permission from metadata service. As you can see here, this will be destroyed. Before we can apply the instance service roles, we need to modify the AWS node daemon set and the service. The reason for that is by default that a service is not, the instance roles for services are not enabled on that service. So we have very simple patch that's been provided by AWS to update that daemon set and that service with specific configuration. And that is the wrong command, so it will error, but we have a fix. All right. So we have to run two commands, two patch commands, one to the daemon set AWS node, and we're gonna show you the patch itself. That's available on AWS best practices website as well. And as you can see, it's quite simple patch. All we're saying is the daemon set needs to have annotation IRSA enabled. And what we need to do for the service account, we need to point to a role that this service is allowed to assume. In our case, we have created this specific role. And if we patch it, and if we redeploy our nodes, the metadata service will be disabled. It will not have permission. So the metadata service is still there. And as I show you in a second, let's just apply our configuration. We need to taint the nodes. The only reason we're tainting the nodes is because we've created them initially, and we want to basically redeploy them. We don't have any production loads on this demo deployment, but this is the kind of one thing to keep in mind, and it's a good thing to deploy these instance service metadata policies early, because otherwise they might be disruptive to your workloads. With Gatekeeper and with network policies, you are not required to kind of redeploy all of your nodes. With this solution, you do, if you didn't apply it in the first place. We're just gonna let it run. And now what we're gonna try to do is show you the difference in permission that the metadata service endpoint has. So we're gonna apply again the same pod. We're gonna just wait for it to deploy. Then we're gonna just exec into the pod. Now we're gonna run two commands. We're gonna show you that the instances still have some permissions, right? So we still have the problem of information leakage. So we cannot run describe network interfaces. We have removed that permission. So the attack will not work because not every pod will be able to simply modify the security groups. However, as you can see, we still can enumerate information. We can still gather information. So it's not full solution. So you're still encouraged to use network policies and Gatekeeper to additionally improve it. But at least you have removed the most impactful policy from all the pods. Okay. And lastly, we really need to enable these logs. And for that, with Terraform, again, it's very simple to enable the logs. All we have to do is remember to, when we configure the EKS cluster, to enable one line more that says enable cluster log types. And we need to include the types of logs that we want to collect. Now, caution with deploying this initially, you need to think about the costs of this. By default, the logs are not kept because you will have to pay the price of storing them on CloudWatch. So whenever you speccing how much running EKS cluster will cost you, and you want to have the logs, and you should really have the logs, you should include them in finding out how much it will cost you to actually run this. So let's deploy the logs. The Terraform in this example thinks we need to update our roles, but in reality we don't. It's just that Terraform thinks it needs to refresh them. So this is quite fast. So what we did, we ran the same attack that we did before. And now we're gonna look in the same path on the trails. We're gonna look at event history. There is this modify event that happened again. We know it's happening on a node, so we're going to investigate this in our cluster. But now if we go to configuration, logging, you can see that API, audit, and authenticator logs are collected. Now, this will generate a lot of logs, and that will cost money to store. As you can see, this is quite noisy. However, it does give you a lot of information of what is going on in your cluster. Luckily for us, AWS has another service called Logs Insights. And that allows us to query the logs for the information we need. And we know that what we're looking for is a resource pod and sub-resource exit, which represents the events of executing in a pod. The only reason we're looking for these is that we're making an assumption that someone has been executing commands. If we are Unsure, this will of course take longer. But what you can see here now is that we found that James Smith was running the command of executing container in our Kubernetes cluster at the same time. And now you can investigate further of like, why did that person need to do that? And you can at least point it to the direction. Now, in reality, if you're using IAM roles and there is a lot of chains in assuming these roles, this might not be as trivial as I demoed, but you can see how much more information you get with logs enabled. Now, so we talked a lot about like 3 major issues of making your API endpoints public, making sure that you have logs enabled, making sure that you don't have too many permissions attached to your logs. So how can Snyk help you secure your cluster? So for that, I have live demo. So I've captured the Terraform plans of we used to create our cluster. And I have some commands we can run. So first command we're going to run is Snyk IIC test on the Terraform plan that we have created. Now, you can imagine how you can use this. You can include that in your PR checks. You can run this every time you're trying to deploy Terraform workloads, and you're going to get some information. So in this case, you get immediate information that your EKS will be publicly accessible and that you don't have enough sufficient logs, right? But we had this third problem of too much permissions. So in our product currently, there is no specific role to target the CNI plugin permission. However, we have a feature where we can enrich our own rules with custom rules. So what we did is we created the kind of custom rule that checks if any role looks for, allows you to assume CNI plugin. And what you can see here, we're saying we detected that use of CNI plugin policy, and you see the resource that is using it. In this case, it's used by our service role for the pod, which is fine. But you can see how you can enrich your information such that you want to do. Besides using it in just CLI, you can also use Snyk with integration in your Terraform Cloud. So if you're deploying your EKS cluster with CI/CD system like Terraform Cloud, you can have it as part of the new feature that they have called task runs. And then you can see the same findings I have just shown you in Snyk UI that will help you to kind of catch these issues, track them over time. They can be included in your reports, and you can share them between people. So that's how Snyk can help you with detecting changes in your kind of cluster creation. But let's be honest, you're not creating clusters every day. It's not what you're going to be using all the time. However, you will be deploying workloads every day. You will be creating pods, and Snyk can help you with scanning those pods as well. So as we saw before, deploying pods with network name and with networking, host networking mode enabled might lead to some exploits. And by running Snyk on every spec that you're trying to deploy, you get the information that we saw in a gatekeeper right there when you're developing. So for example, here, you will not only find that this pod will allow you to do host networking, it will also tell you that we're running as root and you're not dropping capabilities. There's a lot of information that we can give you. And besides being able to scan Kubernetes manifests, we can now, and this is brand new feature, scan your pods if you're using Terraform Kubernetes provider. So as you can see now, just in here, just for demo, we have created the same pod with Terraform provider in very different configuration, but we can use the same tool to scan both Kubernetes native manifest and Terraform manifests for the same information and get it early in your development lifecycle. So this is how Snyk can help you stay on top of these security problems early on. And next steps, we've only literally touched the iceberg of our problems. There is many other things that you should consider. AWS has a very good documentation on best practices on how to configure your EKS service. You can find everything from security to reliability. On security front, it will go much deeper into kind of forensic controls and what else do you need to do to protect your pods. It will talk about everything I've talked about on network policies, kind of admission controllers, and what you can do there to help you. So I would really recommend you to just Google EKS best practices guides from AWS, and you can find all of that information there. And this was the fourth and final session of the 4 days long AWS live hacking. So remember to, if you've attended all four, that you're gonna get email from Snyk to take part in this spin the wheel lottery, and I hope you're gonna be lucky. And that is it from me. So if there's any other questions, I can answer them now. And thank you very much for listening to me. I don't see any question at the moment, but I'm gonna give it a few minutes for people to there is a question of when. Can we get access to source of your demonstration? Of course you can. Let's do it now. So the Zoom. All right. So there's two sources, but what I will do is I'm gonna share everything you're gonna find here. And soon after, I will share the other specific demo. There's gonna be some CTF challenges where you can actually go and try to do these hacks yourselves. Hopefully you're gonna enjoy that too. And the questions in the chat are, when do we receive the email? Someone from my team will reach out to you. I assume it's gonna be soon. Will the all four presentation be available on demand? That's a good question. I only assume that's the case. I didn't get the first part of the problem, reusing the credential used to create a cluster to run pods. This is the inherit permission problem. Well, this is the problem of if you use identity to create a cluster, you cannot remove that identity permission from the cluster. They will always have those permissions. There is literally no way for you to do that other than deleting the identity. However, deleting it does not fix the problem because you can recreate it and it's linked to the name. It's a very interesting problem, which I don't fully understand reasons why it has to be this way, but it's hard coded to the name of the identity, whether it's the name of the role, whether it's a name of IAM user, it always stays there at the moment. Can you share the GitHub link? Look above. Where are you pasting those links? I'm pasting it in the chat. Hopefully you can see them, but maybe it's going to a different chat. Let me make sure that works. One sec. There we go, everyone. I hope these links now work. And another question, do you see we should use EKS for lightweight apps as well as just small EC2 is sufficient? What's your recommendation? When should we use EKS, ECS? It's a good question. If you don't need all of the features from Kubernetes, I think ECS it's a good solution if you have kind of less complex workloads to worry about, because you then don't have complexity of managing nodes. It actually might be cheaper as well. So I, for example, use ECS for small workloads that do not require a lot of kind of scheduling and configuration controls. What else do we have? And can you please share the GitHub link? Thanks, regards. Type answer. Send. Awesome. And I hope everyone is getting the links. You're welcome. I really hope you enjoyed it. Cool.